So we're very happy to continue with Marcia Tenser, who will be talking about Wilson loops and defect flows in ABJM.
Okay, so good afternoon. First of all, let me thank the organizers for giving me the opportunity to talk today. I will talk about Wilson loops and defect RG flows in ABJM, and this is based on work that I have been doing on the past few years in collaboration with Castiglioni, Penati, Trancanelli, and I will also be talking about ongoing work with all of them and Marco Bianchi as well. So this is how I organized the talk. I will start by giving an introduction and a motivation. Then I will present you Wilson loops in ABJM. I will talk about defect RG flows. Then the ongoing part, which is cohomological equivalence and framing. And I will finish with, by pointing out some future directions. Okay, so introduction and motivation. Wilson loops are fundamental objects in any gauge theory. But in particular, when we talk about supersymmetric gauge theory, we have a really special thing that we can play along with, which is the fact that we can construct these operators in such a way that they are supersymmetric. So they preserve some amount of the supersymmetry of the full theory. And the way we do it is to take the definition of the usual Wilson loop operator, where you have the trace of the path-ordered exponential, and the gauge field inside this integral. And we allow matter to appear as well. So if you think of a particle that you are considering to go through some curve in space-time in the presence of this gauge field, you can also think of this particle going along some internal space, which is how you think of the matter fields as well, how you couple these matter fields to the Wilson loop operator. And the cool thing is that when these Wilson loop operators are supersymmetric, you may be able to compute them exactly via localization, and this provides non-trivial tests for the ADS-CFT correspondence. These operators are also seen as defects. They define 1D superconformal defects, so they preserve this group, and you can play with different tools and superconformal bootstrap to study correlators in these defects as well. And finally, most recently, there's the trend of generalized symmetries. And Wilson loops are charged under two-form symmetries, so they may provide topological objects to study non-invertible symmetries. So also, if you think about them as 1D defects, you can also study non-trivial RG flows taking place on them. And this has been well studied in n equal to 4 square Young Mills, where the BPS Wilson loop is as the one I have written there. So you have, again, the trace of the path-ordered exponential. You have your gauge field and the scalar. You put here the scalar. And you can put some parameter in front, which is the zeta parameter, such that when you have zeta equal to 0, you simply have your ordinary non-BPS Wilson loop. And when the zeta is equal to 1, you have the half BPS Wilson-Madasena loop. And a flow happens between these 2 points. So the ordinary loop is the UV fixed point, and the half BPS is the IR fixed point. And you have a non-trivial flow connecting these points. This was studied by Polchinski and Sully and Beccaria-Jombit cycling. And in ABJM, we have an analog situation. But the fact is that in 3D, we have a much richer structure of BPS Wilson loops. So again, we will have some RG flows connecting different representatives, but we have a much richer structure to play with, and I will be showing you today. So here, for instance, I chose 2 points. One UV fixed point, which is 1/6 BPS. So out of the 24 square charges of your theory, you preserve 1/6 of them, and you flow in the IR to the half BPS operator. Okay, so as I promised, I would talk about Wilson loops in ABJM, and we have our operator defined in terms of the gauge field and the matter fields. We need to fix also the contour along which we'll be studying our operators, and we take this to be the circle or the latitude. And for the matter fields, we have different options here in ABJM. We have scalars and fermions connecting the two nodes of the quiver that describes our theory. And the type of operators that we can construct are either one-node loops or two nodes. The one node is bosonic. It's also called a bosonic operator, and it is at most 1/6 BPS. And to define it, we have one of the gauge fields. I took here, for instance, the gauge field on the left of this quiver. And you put the scalars, and in 3 dimensions, which is in contrast with n equal to 4 spring mules, we have scalar bilinears instead of a single scalar. And we put them in such a way that you preserve some amount of the supersymmetry here. So what I denote with this red star is what you tune for your operator to be supersymmetric. If you define a two-node loop that we call fermionic, we can have operators that are at most a half BPS. And in this case, the definition of the operator includes both nodes, so the node on the left, A1, the node on the right, A2, the scalars again, and the fermions in the off diagonal. All of this appearing in such a way that when you act with a supercharge on W, it annihilates W, so you have supersymmetry being preserved. So the game here is to play with these parameters that I always denote as red stars to have SUSY being preserved. And we'll see that they undergo some non-trivial RG flow, and we have the picture more or less analogous to what has been seen in n equal to 4 spring mules. So as I said, ABJM display a much richer structure of BPS operators. And here I show a few of them that are BPS or not. So the way to read these two figures is that on the horizontal line we have bosonic operators, and in the vertical line the fermionic ones. The symbols are such that we try to display the amount of our symmetry that is preserved in an intuitive way. So you have SU4, which is the full group, SU3, or 2 copies of SU2 being preserved. Then in black, non-BPS, blue 1/6, red a half, and in green 1/24. So if we go to the figure on the left, we have here in the middle a bosonic operator that is 1/6 BPS, so it's blue. And we have a green line connecting 2 other fixed points that are a half BPS operators and preserve SU3 because they are triangles. And on the right, we have more or less the same picture, but if on the left we have connecting these 3 points, green lines, so BPS operators, here on the right, all the arrows are black, so you have non-BPS representatives. And here we also have other operators that are bosonic on the horizontal line that preserve different subgroups of our symmetry. So this is only to show you that we have indeed many different operators in ABJM. 3 dimensions, it's much richer. And what we do with this full setting is that we use the 1D auxiliary method to compute the expectation value of these operators. So what we do is to propose a 1D method. So we have this one-dimensional auxiliary fields Z and Z bar. And by computing the 2-point function of these fields, we are able to capture the expectation value of the Wilson loop. This was originally proposed in QCD back in the 80s. And what we did was to adapt it to ABJM. So instead of having an effective action that is the QCD one and the one-dimensional one that we add, we have an effective action that is the ABJM one and an analogous thing of a one-dimensional theory, but with superfields instead of usual scalar fields. With this definition of the effective action, note that here, inside of this action, we insert whatever defines our operators. So the connection with a single gauge field and scalars, or the connection that we call a super connection with the 2 gauge fields and the fermions in the off diagonal. So we use this to compute the expectation value of the Wilson loops, but we also use it to compute the beta functions of these parameters that I told you that we play along with, so the red stars. And what we found is that these beta functions are non-zero, So again, we have an RG flow connecting the representatives. And okay, I will talk about these RG flows. When these parameters are generic, the stars are generic, we not necessarily preserve supersymmetry. So it's generically broken. And the expectation value of our operators will be a function of these red stars, these parameters, that have no non-trivial beta function. So, for instance, if we consider bosonic flows, we have one gauge field and a combination of scalar bilinears. And a plot of a particular RG flow that we have is this one on the left. And I will explain the elements here. So first, we start in the origin with a repulsive fixed point, where an ordinary Wilson loop lies. But in contrast with what happens in n equal to 4, this ordinary Wilson loop includes not only the gauge field, but includes also the scalars. And it includes in such a way that this M matrix, that is the scalar coupling matrix, is plus or minus the identity. When this is minus the identity, we have this point. When it's plus the identity, no, the other way around, plus identity here and minus identity here, we have a fully repulsive or a fully attractive point. And connecting these 2 points, we have this red square, this white square here in the middle, where we have only the gauge field. You don't have the scalar bilinears. And this would be the n equal to 4 ordinary Wilson loop. But as we see here in the picture, it's not a fixed point. It's just a regular point in the flow. And surprisingly, here we also find 1/6 BPS configurations, where M is diagonal with entries -1 and +1. And these are not fully repulsive or attractive. These are saddles. And finally, as I said, this is different from what happens in n equal to 4 Young-Mills. Another thing we can do is to study fermionic flows. So we can start from a bosonic one that is actually a composition of 2 bosonic ones. So we have one node here, one node at the bottom, but no fermions in the off-diagonal. And we deform it. We add some perturbation that allows the fermions to appear in the off-diagonal. And we have a 3-dimensional RG flow as I chose to present it here today. So basically here on the green plane, we have only scalars, no fermions turned on. So this is the analog picture to what I showed before. And so here we have a fully repulsive and attractive, the saddles. And if we turn on fermions, we leave this plane. So we go in the z direction of this plot. And we see that what seemed to be fully attractive or fully repulsive, actually here, in this fully attractive one, you actually flow away. So it's not a global fixed point. And here you flow to a half BPS configuration. So what happens here is that you have supersymmetry enhancement because you have SU3 R symmetry. So you see it's a triangle here. And this operator has been constructed in 2009 by Trancanelli and Drucker. So this is a special fixed point. And another thing we can do when we study these RG flows is that we can constrain these red star parameters such that supersymmetry is preserved. So our RG flow will now be called an enriched flow because every point on this flow preserves some amount of supersymmetry. And what we have here is that we can start from a 1/6 bosonic operator. And we see that we flow away and we reach a half BPS operator here. And we can do that from infinite directions, the lines that come from infinity. And all these points are 124 BPS. Or you can do it in this green line here, along which all the operators are 1/6 BPS. And along this green line, we were able to establish a G theorem. So the expectation value of our Wilson loop operator actually defines a G quantity such that GUV is greater than GIR. And I guess this is what I wanted to say about defect RG flows. And now I can move on to ongoing things about cohomological equivalence. And to give like a smooth transition between the two, I repeat here the plot that I was showing before, because all of these points that we see here in this plot are BPS. And the idea behind the construction of this kind of operators here is that all of them are connected to the central point, so the origin, which is the 1,6 BPS bosonic operator, via some deformation that we studied a few years ago. And this deformation is such that all these operators are expected to be cohomologically equivalent. So this means that every W that we reach in this plane can be written in terms of the origin, W boss 1,6, plus Q acting on some function V, some matrix V. And this Q is mutually preserved by W boss and whichever W you reach with your deformation. So in particular, cohomological equivalence means that the expectation values localize to the same matrix model. So we expect all these operators to have the same expectation value. But as I showed you in the previous slides, these operators depend on these red star parameters. So depending on how you tune these parameters, you have a different expectation value. So what is happening? And this is what we are investigating now. The idea is that this red star dependence could possibly be cancelled by framing the Wilson loop. The reason why we thought about it is because perturbation theory, which is what we did so far, is usually performed at framing 0, whereas the exact result holds at framing 1. So the idea is to generalize the perturbative computations to incorporate the effect of framing. So here is a small parenthesis to explain to you super fast what framing is. So framing was something that was observed first in Chern-Simons theory, so a purely topological theory, where the expectation value of the Wilson loop was seen to be a non-topological invariant quantity, but it became topologically invariant if and only if we frame the contour. So the expectation value of the Wilson loop has to take into account this F, which is the effect of framing, that combines as a phase such that it becomes a topological invariant of the theory. And the way I think of it is if you take this knot, the blue knot here, you have these arrows, so this bundle here, and it's like counting how many times it goes around the blue ribbon as you go around the closed knot. So this is the form of this topological invariant. This is how you compute it. You have the contour C and the framed one. And by performing this integral, it basically spits out some integer that is counting basically how many times these arrows go around when you close the path. And the fact is that even though ABJM is not topological, because you also have matter, nevertheless, the expectation value of the Wilson loops are sensitive to framing. So the first question is, can we compute this VEV perturbatively at generic framing? And this is what we are trying to do. So we are using what we call point splitting. So we define an helix going around the circle n times. So we have here the circle, the blue curve, and we parameterize this yellow curve here that goes around it. And we do it in such a way that we count how many times it goes around, and we expect this number to be the framing, the analog of framing. Once we take this deformation delta to 0, it should spit out the framing. So in particular, doing the perturbative computations, we see that this VEV is sensitive to framing not only via the gauge field, as in the Chern-Simons case, but also via the matter contributions. So when we compute each Feynman diagram using point splitting, we need to take into account gauge propagators, but also matter exchanges as well. So this is what I want to show you in the next slide. Sorry, how am I doing with time? 5, okay. Okay, I chose a couple of nice plots, of course. And the idea is to show you different behaviors regarding framing. So here I chose 2 different fermion exchanges at 1 and 2 loops. So here on the left we have a single fermion exchange, and we see a behavior that as we increase the number n of our yellow curve that goes around the circle, we see a linear behavior in the framing contribution. Whereas if we go for 2 loops and a double fermion exchange, as we increase n, we see a squared, n squared behavior. And well, this is nice. It's a nice result. Says that we are going in the right direction. But these diagrams all come with these red star parameters. So even though we are keeping framing under control, we are seeing how it behaves for each diagram, we don't really expect a red star dependence. This is actually what we want to get rid of, because we expect cohomological equivalence to make all these VEBs collapse to the same expectation value. So this is the second question. What about the dependence on these parameters, red star? And the interesting thing is that it seems to drop out for f equal to 1, which corroborates with the assumption that f equal to 1 is actually the nice framing value and the value where the exact results hold. Finally, I will point out some future directions. First of all, I think it's super interesting to investigate the origin of the conformal anomaly that is driving our RG flows. Then, about the gravity dual of ABJM, which is M theory on ADS4 times I7 mod ZK, or for large enough A, K, type 2A string theory on ADS4 times CP3. I must say that the strong coupling description of these Wilson loop operators is not completely known. And one interesting thing that could be pursued is the topic of interpolating boundary conditions on CP3. This is also inspired by work by Puczynski and Sully and has been carried out in the context of CP3 by Correa and company. So the idea is that these Wilson loops, as I said, provide non-trivial tests for the ADS-CFT correspondence. So on the CFT side, we have our Wilson loop. On the ADS side, we have some corresponding string or brain configuration. And depending on the amount of supersymmetry that our Wilson loop preserves, we have some different boundary conditions here on ADS. So for the half BPS operator, we have Dirichlet boundary conditions. For the 1/6 BPS, we have Neumann on 2 of the CP3 and Dirichlet on the rest. But for all these interpolating points connecting our flow, it's not clear what are the boundary conditions and if we can find the solutions satisfying it. So this is what I wanted to say, and thank you.
Questions?
Can you pick a previous slide? I think I have a question related to the first point, and also more generally, you had this RG flows, but what induced this RG flows from one point to the other, and what do you mean by conformal anomaly at that point?
Okay, so what I mean by the conformal anomaly is the fact that, in particular, when we are dealing with these enriched flows, where every point is BPS, we expect that at the quantum level you still have conformal symmetry holding, but still you have a non-trivial RG flow. So at the quantum level you have some anomaly that would trigger you to go from one point to the other. This is what I mean.
And then when you had the diagrams, and where in a sense you had the fixed points, so if you're sitting in a fixed point, what makes the serial run? What did you do?
Okay, it's this. For different diagrams, I use different operators that are the deformation that we consider. But here, for instance, you can see clearly that we start from this point, and the deformation includes something that has the scalar bilinears, so you're changing this M, and it also includes the fermions in the off-diagonal. So this is what you are using to trigger the flow, to leave the origin and flow wherever you want to.
What's the definition of the G function in terms of the Wilson line operator?
It's the expectation value of the Wilson line.
Okay, and how does it count the effective number of degrees of freedom in the theory? I understood that that's typically the interpretation of the G function.
Okay, that I will have to think about. Sorry.
So there's another class of loop operators in these theories, vortex loops. Is it possible to repeat this entire analysis for vortex loops?
I have no idea. But that's an interesting question.
You're relying on an electric Lagrangian description for the operator in order to do the RG flow?
Yeah.